All right, so now that we spent some time talking about retractions, we're now ready to go back to the question of line search methods. Okay, so in particular line search methods on Riemannian manifolds. Right, so if you have so a line search method on a manifold, right, has an update formula of the following form. So the new candidate point, right, is equal to the retraction based at the O point applied to some step size, if you will, time step tk, and some search direction. Okay, sort of eta k. So where you have a search direction, which is in the tangent space at xk to m, and you have some scalar, which is a time step. So if we recall, right, the reason why we had introduced a retraction is because even though in principle you have a Riemannian manifold and a Riemannian manifold is endowed with a Riemannian exponential, in practice a lot of times it's very expensive to compute the Riemannian exponential because it's formally defined in terms of the solution of some differential equation. Okay, and so if you want to construct practical optimization algorithms on oftentimes matrix manifolds, then you might want to choose something which approximates the exponential, but in such a way that it doesn't compromise our ability to prove that the line search algorithm converges at a certain rate. Okay, so what we're going to do then is that, so the definition of the retraction, in particular the rigidity condition, right, is a way of, it's like capturing the essential properties, if you will, of the Riemannian exponential, which end up being critical in trying to prove that, these line search algorithms actually converge. Okay, and so now we're going to ask sort of a similar question, not for the retraction, but for these other two pieces, right, which is the time step and essentially the search direction. So what properties of the search direction we have here, right, would guarantee that you have an algorithm that eventually converges? What property of the time step which we choose will eventually give you a numerical method which converges? Okay, so that's the question we're trying to ask, right? So let me just state that. So once the retraction is chosen, right, the remaining issues are to pick the search direction and the step size. And then in order to guarantee that you have global convergence, we need some conditions on these things as well. Right. Okay. All right. So the first thing is that these search directions don't exactly have to be the gradient. Again, it's sometimes the case that it may be expensive to exactly compute the gradient, but you want to have it be what is called gradient-like, which more or less has to do with, it's like, so the gradient is this direction of steepest sort of ascent, right? And what you want basically is to have the property that while you don't necessarily have the direction of steepest ascent, you have some control. It's like over that rate of ascent, right? So, so this leads to the idea of what are called gradient-related sequences. So let me just define that for you. And of course, the whole reason it's like to, try to enlarge the class of choices we have, right? In constructing these line search algorithms, and we've done this by, instead of just looking at Riemannian exponentials, we've looked at retractions. Instead of looking at just the gradient, it's like we're going to look at what are called gradient-related sequences, and instead of just picking some fixed step size, we have a condition in that. And so of course it's like the idea then is that you want to relax the conditions on each of these individual things. It's like, well, still allowing you to prove a global convergence result. And the goal obviously then is that by increasing the sort of design choices you have, it's like, you can develop a larger class of algorithms, all with the same provable sort of guarantees. It's like on global convergence. Yep. Okay, so anyway, so this is the idea of this gradient-related sequence. So if you're given a cost function, let's say f, on a Riemannian manifold, and if you recall, it's like the reason, of course, why we need the Riemannian manifold structures to even talk about things like gradients, right? So a sequence of search directions, if you will, or candidate search directions, right, where these things are in the appropriate tangent spaces to the manifold. Right, is gradient related right, if for any sequence, any subsequence, xk, k is in some sort of index set, big K, of the original sequence of iterates that converges to a non-critical point, so a non-critical point is basically the point where the gradient doesn't vanish, right? The corresponding sequence, it's like of these things. Corresponding subsequence, right? Where K is now in the same index set, right, is bounded and satisfies condition as follows, that the lim sup as K goes to infinity, where K is in this index set, right, of the gradient of fxk with this thing with the search directions are negative. Okay, so more or less it's like the what the intuition for all of this is that so you want this thing to be essentially bounded away from zero. It's like in some sort of limiting sense, okay? And the reason, if you will, is that you don't want a situation where the search directions, it's like end up being in some sense perpendicular. It's like to the gradient directions, right? right. Okay, so and the reason for this, of course, is and also you also don't want this thing to vanish, right? Um, and the reasoning behind this, of course, is that if you had a situation, say hypothetically, it's like where this thing actually becomes zero, right? Then there's several possibilities. One of which is that it's like the search directions are orthogonal to gradient, or the other sort of obvious possibility. There may be more possibilities, but the other obvious possibility is that this, it's like sequence is actually sort of going to the zero vector, which is not what you want because it's like you have a sequence of points. It's like xk. It's like which are converging. It's like to a non-critical point. So you don't want the algorithm. It's like to stop there. Whereas it's like if you had if you sort of violated this lim sup condition, it's like then what could very well happen is that it's like the line search algorithm or line search method which you implement, it's like using this particular sequence, it's like of search directions, could actually end up could basically end up it's like just not converging, it's like to this non-critical point, which is obviously not what you want. Okay. All right. So the other property is sort of about the choice of step sizes, and if you've ever done sort of line search algorithms, then you might have heard of this sort of the Armijo line search, which is related to this notion of sufficient descent, right? So more or less the idea, if you will, is that if you know something about the gradient tells you it's like in some sense, it's like the gradient gives you some sort of linear model. It's like of how, it's like the cost function is decreasing. It's like locally, and you want to compare the actual, it's like descent which you have in the cost function by evaluating, it's like the cost function at a new candidate point with what you would have expected. It's like just based on the gradient, right? And the basic idea, if you will, is that if the descent you have, it's like is sort of comparable, larger than what you would expect from the gradient, then you can sort of keep going, and if not, it's like you might want to take a smaller step size. Okay, so this Armijo point and this Armijo sort of line search condition is related to sort of picking sort of the appropriate, it's like step size, so that again you're guaranteed to converge. So let me give you this definition of the Armijo point. So if you're given a cost function f on a Riemannian manifold, M with retraction R, right? A point x on the manifold, tangent vector or search direction, and scalars A bar, which are greater than 0, and B and sigma, which are in the open interval between 0 and 1. Then the Armijo point is the following. So it's t to the a times eta, right, which is beta to the m alpha bar times eta. Sorry, not t to the a, it's a ta. So this is the Armijo step size, and then this is the Armijo point, right, where m is the smallest non-negative integer, such that the following is true, that the function value at the initial point minus the function value at the candidate new point, which is obtained by, again, applying the retraction to, it's like appropriately scaled, it's like step in the direction, the search direction, right, which is beta to the m a bar eta, right, is greater than equal to minus sigma multiplied into the gradient of f of x times b to the m a bar, it's like eta at a point x. Okay, so again, the idea is to compare the actual descent which you have, right, from the initial point to the candidate point to what you might expect based on the gradient. Okay, yeah, and if again it's like if it's the case that you have sufficient descent, then you're good. Okay, and then the real valued TA, which is of course just beta to the m a bar, right, is the Armijo step size. Okay. All right. So as you might expect, then it's like this is setting you up for a situation where you want to construct a line search algorithm on a Riemannian manifold. It's like by using sort of this update that xk plus 1 is r at xk applied to this direction, right? And you want the step size obviously to be one of these sort of Armijo step sizes, and you want the search directions, it's like to be these gradient related sequences, right? So that's basically obviously where we're heading towards. Okay. So of course, another possibility, it's like with line search methods, which is mentioned in the book, obviously, is that instead of this Armijo line search type method, it is perhaps possible to also do what are called exact line searches, right? So what one means by that is that it's like you look along, it's like this curve, it's like which is defined by this retraction, it's like in the search direction, and it's like that converts and you evaluate a function along that curve, right? That gives you then a scalar. I mean, it's like a sort of an optimization problem, which is one-dimensional, where you're searching over one-dimensional parameter, and you could potentially try to choose the line. Choose the step size. It's like by trying to minimize that exact line search. Okay. So anyhow, right. So let me just at least state a possible line search algorithm with this in mind, and then we can discuss this further. Right. Maybe I'll erase everything, just so that we have space to write down the algorithm. Okay, so this is the algorithm for an accelerated line search. Okay, so you require the following things, right? So you need a Riemannian manifold, M. Right, some continuously differentiable cost function. F on M, a retraction, R, which is a map, if you recall, from Tm to M. Right, and then you need the parameters of this Armijo line search, right, which are that A bar is greater than 0, if you recall. Then you have C, beta, and sigma, which are in the open interval from 0 to 1. And then you also need as your input the initial point for your line search method. So your initial iterate, x0 in the manifold, and then the output is a sequence of sort of iterates on the manifold, right? Okay, so so now we're ready to sort of talk about what the algorithm is. So for k equals to sort of 0, 1, 2, and so on, do the following. So you pick sort of eta k in txk to the manifold, the tangent space at xk to the manifold, such that the sequence is gradient related. Right, we had just discussed this, and then you choose a new point, xk plus 1, right, which is this Armijo point in that particular search direction. So such that f of xk minus f of xk plus 1, right, is greater than or equal to c times f of xk minus f of rxk tk a eta k. All right, where TAK is the Armijo step size, for the given alpha bar, beta, sigma, and eta k. Okay, and then you end the for loop. Okay, so what this algorithm is doing is not directly using, it's like the line search method we had discussed, it's like earlier on manifolds, right? So the candidate, it's like which would have come from that retraction-based line search would have been RxK TKA eta k, right? So this would have been the candidate sort of step, right? And of course, you know, it's like this algorithm would, you know, I mean, it's like, so xk plus 1 actually being equal to this would clearly, it's like satisfy this inequality which we want, right? So I should say the remark is that, right, xk plus 1 actually being equal to rxk tk Armijo, it's like in the search direction would clearly satisfy the inequality. All right, and then sort of would be a suitable example, it's like of an update. But again, the point, you know, it's like in this discussion is to try to be as flexible as possible and allow you to look at algorithms which again are as large, you know, it's like as possible. It's like while still it's like having a global convergence result, right? So the basic idea, if you will, is that you know, you want to have the flexibility that you don't actually use this this update, but you want to basically, you know, it's like have that this sequence, it's like it's comparable, it's like, or it does as well or sort of better, or at least up to some sort of fudge factor, right? As this sort of more exact method. And the basic idea is that if you have an k sequence which satisfies this inequality, you can use, it's like what we're about to prove, it's like for this update to then say that this method also converges. Okay, so so maybe this is a good time to stop. It's like, and then we'll discuss a little bit. It's like how to go about proving convergence. It's like with a sort of slightly enlarged class of algorithms. Okay, so let me stop here.